Have you ever wondered about the hidden language that powers, well, pretty much everything? From the logic inside your computer to the way mathematicians build entire worlds of thought? Today, we're going to pull back the curtain on that language, set theory. It is the absolute bedrock for so much of our modern world, and it all kicks off with a beautifully simple idea. I mean, seriously, think about it for a second. How do we make sense of everything? We are constantly taking all this information flying at us and sorting it into neat, understandable little piles. And the thing is, we do this instinctively, every single day, without even thinking about it.
You do this all the time. When you make a grocery list, you group things, right? Dairy, produce, snacks. You build a workout playlist by grouping songs that have the right vibe or tempo. Even something like all the students in your school, that's a group. These are all just real-world examples of the one core idea we're talking about today.
All right, so here's our game plan. We're going to start with the absolute basics. What is a set? Then we'll see how to talk about them and even draw pictures of them. After that, we'll check out how sets relate to each other, how we can combine them, and this is the cool part, how all this abstract math is actually powering your computer right now. And just for fun, we'll wrap up with a paradox that literally shook the foundations of logic.
Okay, first things first. What exactly are we talking about when we say a set? Well, you can think of it as the atom, the fundamental particle that everything else in discrete math is built from. And it's an idea so simple, you honestly already get it.
So here's the official definition. A set is just an unordered collection of distinct objects. We call those objects elements or members of the set. That's it. A set is basically just a container for its elements.
Now, there are two super important rules that make a set different from, say, just a list. Rule number 1, the order of the elements doesn't matter at all. The set with 1, 3, and 5 is the exact same set as the one with 3, 5, and 1. And rule number 2, duplicates get ignored. If you write down an element 5 times, it only counts once. The set is still just 1, 3, 5.
So how do we actually talk about and work with these things? Well, mathematicians came up with a really clear language and, even better, a way to draw pictures of sets that makes all this abstract stuff feel way more real.
You've got two main ways to write down a set. The first is called the roster method, and it's as easy as it sounds. You just list all the members. For example, the set of vowels, V, is just A, E, I, O, U. Simple. The other way is set builder notation, where you just define a rule. You could say, my set contains any x where x is an odd positive number less than 10. Both ways get you to the exact same set, they're just different paths to get there.
And to help us see these ideas, we have this guy to thank, the English mathematician John Venn. Back in 1881, he came up with a totally brilliant and simple way to draw sets and see how they relate to each other.
And his idea is just so clever. We draw a big rectangle, and we call it U for the universal set. Think of it as everything that could be in our set. In this case, maybe all the letters of the alphabet. Then, inside that box, we draw a circle for our specific set, V, which is just the vowels, and the elements A, E, I, O, U are just little dots inside that circle. It's a fantastic way to visualize what's going on.
Okay, this whole idea gets way more powerful when we start looking at the relationships between different sets. Because it's not just about what's inside one set, but about how different collections of things can overlap and interact with each other.
This brings us to the idea of a subset. It's pretty straightforward. We say that set A is a subset of set B if every single thing in A can also be found in B. For example, if you have the set of odd numbers 1, 3, 5, 7, 9, that's a subset of all positive numbers less than 10, because, well, every one of those odd numbers is also a positive number less than 10.
And of course, we can draw this. With a Venn diagram, if A is a subset of B, you just draw the circle for A completely inside the circle for B. It's a really clean, intuitive way to see that everything in A is also hanging out in B.
And now for the really fun part, operating on sets. You know how you have addition and multiplication for numbers? Well, set theory has its own toolkit for mashing sets together and pulling them apart. Think of these as your logical power tools.
First up is the union. You'll see it with this big U symbol. The union of set A and set B is just a new set that includes everything from A, everything from B, and anything they happen to share. It's the all-inclusive combination. In a Venn diagram, the union is super easy to spot. It's just the entire shaded area of both circles put together. If an element is anywhere in that shaded zone, it's in the union. Simple as that. Next, we have the intersection, which uses an upside-down U.
The intersection of A and B is the set of elements that A and B have in common. It's the overlap, the common ground, the stuff that belongs to both clubs at the same time.
Visually, the intersection is just that little shared space where the two circles overlap. Only the elements that exist in both sets simultaneously get to be in the intersection.
So at this point, you might be thinking, okay, this is kind of neat, but so what? Why does this matter? Well, get this. This abstract math is actually running inside your computer billions of times a second. Let me show you how.
So how on earth do computers deal with sets so fast? It's actually an incredibly clever trick. First, they take a universal set, let's say numbers 1 through 10, and they lock in the order. Then, any subset can be represented by a simple string of ones and zeros. A 1 means, yep, that element is in the set, and a 0 means, nope, it's not.
And this is where the magic happens. Look at this. Set A, the odd numbers, becomes 1 0 1 0 1 0 1 0 1. Set B, numbers 1 to 5, becomes 1 1 1 1 1 0 0 0 0. Now, what if you want the intersection? The computer does a bitwise AND, which only keeps a 1 if both strings have a 1. Boom, you get the bit string for 135. For the union, it does a bitwise OR, which keeps a 1 if either string has a 1. This is unbelievably fast, and it's a huge reason why set theory is so important in computer science.
So far, set theory seems pretty clean, right? The rules are simple, the logic is solid, but sometimes the simplest rules can lead to the most profound, brain-melting questions you can imagine.
Meet Bertrand Russell. In 1902, this philosopher and mathematician was just thinking about the basic definition of a set, and he came up with a deceptively simple question that found a deep, logical crack, a paradox in the whole system.
This was his idea. Just imagine a set, and the only rule for getting into this set is that you must be a set that is not a member of itself. Now, most sets are like this. The set of all vowels, for example, isn't a vowel itself, right? So it would belong in Russell's special set. So far, so good. And here is the paradox. Just think about it for a second. If this special set does contain itself, well, then it violates its own rule, because it's only supposed to contain sets that don't contain themselves, so it has to be kicked out. But wait, if it doesn't contain itself, then it perfectly meets the criteria to be a member, so it should be in the set. It's an impossible, brain-breaking loop. It's a question that shows the beautiful, bizarre limits of logic, all sprouting from the simple idea of a set.